In this section, we will discuss another seemingly strange property of quantum mechanics. Whereas in classical mechanics, one can create an impenetrable barrier, in quantum mechanics, there's always a finite probability of a quantum particle getting through a barrier. Let's consider a roller coaster obeying classical physics, where the height of the roller coaster represents its potential energy. If the roller coaster starts at position A from rest, then by conservation of energy, its total energy is represented by this constant line, and the kinetic energy that it gains is given by the difference between that constant and the height. Thus, the roller coaster will accelerate from A heading towards B, reaching its maximum velocity at its lowest point, then climb towards D, but only ever making it to C. Thus, we expect this classical particle only ever to be found between A and C. Even though the roller coaster has enough energy to be at point E or beyond, it doesn't have the kinetic energy to get over the barrier. The important barrier energy for this roller coaster, then, is given by the energy of the point D and the total energy of the particle given by point A. In quantum mechanics, on the other hand, there is always the possibility that the roller coaster could tunnel through the barrier and reach the other side. We shall see that this is very rare for classical particles and due to a leaking of the wave function through the barrier. We will demonstrate this effect in quantum mechanics by considering a simple rectangular barrier of height v0. The particle will be represented by this wave function traveling to the right incident upon our barrier. We expect there will be a reflected wave traveling to the left, and consider the possibility of a transmitted wave traveling to the right on the other side of the barrier. Because the barrier energy is finite, we will require that the wave function and its first derivative be continuous throughout, in particular at the boundaries. For the solution of this tunneling problem, we will solve the Schrödinger equation for each region of this problem independently, and then use boundary conditions to make sure that the solutions are consistent across the boundaries. The potential energy V as a function of x is 0 in region 1 and also 0 in region 3, and reaches V0 only in region 2. In region 1, V is 0, and so the solution to our wave function of region 1, or psi sub 1, is the free electron wave function we have seen before, given by a wave moving to the right with positive k and a wave moving to the left with negative k, where the relative contributions determined by the prefactors a1 and a2, generally complex numbers, are as yet unspecified. What is required is that the wave vector of either of these two waves be related to the energy such that h bar squared k squared over 2m equals the energy of the particle. In region 3, we have a very similar general solution where because v equals 0, we have the same condition relating the wave vector k and energy, and because we are interested in a transmitted wave moving to the right with no wave coming in to the left, we only have one arbitrary constant c to consider. The Schrödinger equation we need to solve in region 2 is very similar to that in region 1, especially once we recognize that this term here is simply minus E minus V times psi. And because V is a constant, the general solution will look very similar to region 1 with E replaced by E minus V. So the solution will look like h bar squared k squared over 2m equals E minus V, where because our energy is less than the barrier height, we will have E less than V, and so this will be a negative number. Well, if E minus V is negative, that means k squared needs to be negative, or that the wave vector k has to be imaginary. Since we don't want to deal with imaginary k vectors, we will instead substitute alpha equal to I times k. That will enable us to have alpha being a real number solving our Schrodinger equation. This will allow us to flip the sign of our solution such that h bar squared alpha squared over 2m then is equal to v minus e, where v minus e is now a positive number. Substituting alpha equals ik into our wave function then replaces ik in the exponent, giving us that our psi in region 2 is simply exponential increase alpha x or a exponential decrease minus alpha x. Now we have our general mathematical solution to our Schrodinger equation for our square potential barrier problem, where we notice that we have wave-like solutions in both the regions where the kinetic energy is positive or E minus V is positive, whereas in regions where the kinetic energy is negative, we don't have wave-like solutions, but instead a wave function that decays exponentially. To solve for the transmission through the barrier, we will need to solve for the prefactors A, B's, and C using the boundary conditions at the transition at x equals 0 between region 1 and region 2, and also at x equals a between region 2 and region 3. The first boundary condition is that psi is continuous at x equals 0, and that means that if we plug in x equals 0 in psi 1, that should be the same value as plugging in x equals 0 in psi 2, such that the wave function is continuous at the point x equals 0. Well, x equals 0 is very convenient because e to the I kx when x is 0, e to the 0 is always 1, and so the exponential parts cancel out for both region 1 as well as region 2. And so we will simply get that a1 plus a2 then needs to be equal to b1 plus b2. That gives the simple condition down here. And then at x equals a, we need to do a similar thing for the boundary between region 2 and region 3, where this time, though, because x equals a, we need to keep the exponential e to the alpha a, e to the minus alpha a, and also e to the ika for region 3. This gives simply b1 e to the alpha a plus b2 e to the minus alpha a, and then c1 e to the ik times a. We then get two more boundary conditions for d psi dx being continuous because the potential is finite. And so that means the slope at either of these two boundaries must be continuous. Taking the x derivative in psi 1 brings down an ik for a1, but a minus ik for a2. Then again, because the exponent when x equals 0 is simply 1, we get simply ika1 minus ika2 for the region 1. And then for the derivative of region 2, we again bring down either a alpha or a minus alpha to give us alpha b1 minus alpha b2. Similarly, at the boundary x equals a between region 2 and region 3, for the first derivative, we have alpha b1 e to the alpha a minus alpha b2 e to the minus alpha a equal to ik c1 e to the ika from region 3. These four boundary conditions give us four new equations, which is sufficient to solve for the intensity of the transmitted wave relative to the incident. Mathematically, the transmission probability is equal to the probability of the transmitted wave divided by the probability of the incident wave given by the absolute value squared, which for these waves is given by the ratio of the coefficients c1 of the transmitted wave and a1 of the incident wave. After much algebra, we find that the transmission has a simplified form where the transmission is proportional to e to the minus 2 alpha a, where we saw that the exponential decay wave function went as e to the minus alpha x, and we needed to use the x equals a boundary condition. Thus, we have shown that quantum tunneling depends exponentially on two important features of this barrier. The first is the width of the barrier A, and also the height of the barrier in terms of the classically forbidden energy range, the difference between the height of the barrier and the total energy of the particle. Here we summarize the mathematical solution to the previous tunneling problem, where the probability of tunneling is given by this function using the hyperbolic sine function, which includes the exponent of alpha a. And then we take the approximation for when alpha times a is much greater than 1 to give us the simplified form of transmission is simply due to an exponential decay of 2 times alpha times a. Because the particle must either be reflected or transmitted, we have a reflection coefficient which should simply be 1 minus t, such that our solution for transmission of the quantum particle also gives us a solution for the reflection. The physics of tunneling has been used in microscopy to see extremely small features. We will see that electrons in a metal behave like free particle, having free particle-like wavy wave functions. While these electrons don't have the energy classically to escape into the vacuum, their wave functions will decay exponentially at the surface, allowing them some probability in the vacuum. If we then bring a second metal close enough, we can collect some of that probability wave function, making a potential barrier like the form we solved. And so the number of electrons collected in the second metal should be proportional to the tunneling probability through this barrier. In tunneling microscopy, our second metal is a very fine-tipped probe where, as we scan this probe tip across the surface, we can see the atomic roughness of the sample. Because tunneling is so exponentially sensitive to the distance between atoms, as we scan this tip, we will see the tunneling current rise and fall as the surface rises and falls. In this way, tunneling microscopy can see the hexagonal honeycomb structure on the surface of graphite, as well as the individual carbon atoms at the vertices.